So hi everyone, and I want to thank first the organizer to give the opportunity to everyone to this great conference, especially in person. And so today I will present you the results on the pilot survey I performed on the multiplicity of northern massive stars, in particular O-type stars. And so first, a little introduction on massive stars, even if we had already a great introduction from Emma and Evgenia yesterday. So the massive stars are stars that have an initial mass of at least 8 solar masses. And for O-type stars, this limit is actually at 16 solar masses. And they have an important impact on the host galaxy by creating heavy elements when they are dying, and with the cosmic rays that they are emitting both during their life and at the end of their life. And they are also the progenitors of objects at the origin of gravitational waves, such as black hole binaries. So massive stars have a really short lifetime compared to other stars and short formation timescale, and they are rare, which means that they're relatively far, so typically 2 kiloparsec, which makes them difficult to observe, especially during their forming process, because they are still embedded in dust and gas when they reach their main sequence. So with all that, the forming mechanism of massive star still unknown nowadays. And so why do we want to study the multiplicity of massive stars? Well, first, all the studies show that massive stars, well, most or all the massive stars are in multiple systems at some point in their life. And the different model in discussion currently have different outputs in multiplicity characteristic. So for the main model that I show here, for example, for the characteristic of the relation between the separation of companion and the total mass of the system, we have for the core equation model, which use a massive disk, equation disk to form massive stars. This model predicts a correlation between the separation and the total mass of the system. For the competitive equation model that will combine the gravitational potential of close protostellar cores to attract matter further than individual gravitational potential from those cores. So this model predicts that the separation will be proportional to the total mass to the power of -2. And for the third model, the collision model, which uses the collision between two intermediate mass stars to obtain a more massive stars. This model predicts that the separation and the mass are not correlated. And so by studying the multiplicity of massive stars, first we can actually constrain the formation models, but we can also measure the dynamical mass of the components of multiple systems by characterizing their orbits, and we can quantify the evolution paths, which help us predict how they will end their life. And to do so, we use mostly multiplicity and companion fraction, separation and eccentricity distribution, and flux ratio, which give us some information on the mass ratio of the system. And so now, why do we want to use optical long baseline interferometry to study the multiplicity? Well, first we can see on this scheme, which is adapted from SANA 2017, that the long baseline in interferometry is the only one that can fill the gap of separation ranging between 1 and 50 milliarcseconds. And so the orbit techniques is a fast technique to detect companions, which because we only need typically one observation, as opposed to the spectroscopy, for example. And with the OLB technique, we have a direct measurement of the flux ratio between the components of a multiple system. Then the period range that we probe with the OLB technique is more suitable for a follow-up to get the orbital measurements than direct imaging. And for the shorter period companion, the OLB technique overlaps with the spectroscopic techniques. And using the combination of the two techniques, we can measure dynamical mass of components in multiple systems. And so we've shown below the figure some example of already performed survey on multiplicity of massive stars. And we can see that there is already a survey that has been done, which is the SMASH Plus survey by Uxana. So this survey combines the sparse aperture masking and the OLB techniques, and it gave a really better understanding on massive stars, but it couldn't get a hard conclusion on the formation models. So the goal of the pilot survey that I present today was to show that we could perform a similar large survey on O-type stars with the improvement of sensitivity Ashara brought by the Merkix instrument. And so at the time of the survey, Merkix was still in commissioning, and the advertised limiting magnitude was of 6.5 in the edge band. And we can see on the top figure here that for 6.5 magnitude in the near infrared, that gives us about 50 O-type stars observable by Shara, so shown in orange here. And but the theoretical limiting magnitude of the Merkix instrument that was not proved yet was of h equals 7.5, and we can see that with 7.5 limiting magnitude, we can get more than 100 target observable by Shara. And so if we could reach the theoretical limiting magnitude with Merkix, we could actually double the statistic of the SMASH Plus survey, and so get a better constraining the formation models. And so the result of the observation campaign that we did was that we got good enough data on 27 systems, and with shown on this figure the distribution of magnitude. So in green, the one that we observed, in orange, the one on the list on the pilot survey. And you can see that we observed actually a few systems around the limiting, the theoretical limiting magnitude of 7.5. That was our goal for the large survey, showing that actually the large survey is possible. And so to get the final results on our data, we worked on the automatization and systematization of the reduction and analysis of our data. So we worked for a long time on a strategy to get homogenic reduction data, because the reduction pipeline was still young when we started the survey. And I worked with Antoine Méran on the automatization of the analysis of the reduced data using Candid, because Candid, so it's a software made by Alexandre Galen and Antoine Méran, which allow to extract the binarity information in interferometric data, but it was not made to get a systematic analysis on such a number of systems. And so all of this preparation was made to prepare for the large survey that would actually have to analyze 100 of systems. So for the final results, out of the 29 systems that you observe, we detect companions in 17 companions in 15 different systems. So with on this figure shown the difference in magnitude between the companion and the main component, and in the y-axis the separation of this companion. And within this 17 companions, 10 of them are detected for the first time. And this gives us a multiplicity fraction of 0.53 and a companion fraction of 0.59, which is relatively consistent with the smash place survey if we take into account the differences between those two surveys. And so in the information for the formation processes, I give here two examples of physical characteristics that could give us answer. And so on the left, we have the mass ratio distribution Q. And we can see that it is not conform to a uniform distribution, but is it a power law or a bimodal distribution that we can't say yet. And on the right, we have the mass ratio as a function of the physical separation in astronomical units. And we can't distinguish any obvious relation or correlation between those two parameters, because actually for both these parameters, we have too low statistics to conclude on the formation process, which is not surprising. And it shows that we actually need the large survey and certainly also to combine the results of the large survey with a smash place survey to get constraints. On a side note, so in the detected companion, we have 10 systems with an estimated period of less than 10 years, which is suitable for follow-up with interferometry to determine the orbits. And we computed the possibility of Gaia to actually determine by itself the characterization of the orbits of multiple systems. And I show on the figure with the photocenter shift mu as a function of the estimated period. We can see that about 4 of our detected systems should be Gaia, when Gaia DR3 will be out, it should be able to determine the orbital parameters. And so here is my conclusion slide with what I talked about. And so I thank you for your attention, and I will be glad to answer all your questions.
Thank you very much. Are there any questions in the room? Yes, there's one there.
Hi, thank you for the talk. Very nice. For the part of this systematic revision with candidate of the binary candidate. So how you gonna manage to label as a or tag the candidate of binary? I mean, you put a threshold of the number of sigma of the detection map, or you always use, for example, only visibility or visibility plus closure phase? How do you deal with that in the?
No, so for the systematization, I use always both visibilities and closure phases. And in the candidate software, it is common to use the n sigma that it gives, so the significance of the companion detection. It is common to use n sigma of 5 to have confirmed companion. And between 3 and 5, it would be a candidate that would need some more data to be sure that it is a companion, or if there is no companion. So for the detection, we take the n sigma of 5 to get our limit on the detection to confirm it.
There's a question in the chat by Mathieu Defeuillot. Is your comparison to the SMASH survey constrained over the same detection space in mass ratio and separation? If so, what is the parameter space? What is this?
Yes, so that's a good question, because actually the SMASH survey, as I said, was combining interferometry and space aperture masking. And so the range, as it was using VLTI, was from 1 millisecond separation to 200 millisecond separation. When for our own survey, the detection range is between 0.5 millisecond and 50 millisecond. So yeah, we took into account those differences and tried to compare the result of the SMASH Plus survey within the parameters of matrix.
Okay, so let's thank Cyprien again.